Okay, so in this video we're going to take a look at superposition of charge specifically, and we're going to be doing it with charges which are stretched out in a line. And in this particular example, we want to know where we're going to be placing a third charge such that it remains in equilibrium or that there is no net force. So because we're talking about forces, we look at this interaction from perspective number 2, which is a study of forces. And in setting up our problem, the very first thing that we need to do is we need to decide where should we be placing this third charge. Now there's a couple things of importance to take note of. The first is we don't know what the sign of the charge is. And the other thing is, we don't know the magnitude of that charge. So the only conclusion that you should probably draw from that is that they're not needed, because that's not a value that you could look up, like say a physical constant or a geometry equation or something like that. You know, sometimes we are tasked with resourcing information which is understood that you can look it up, and that's not the case here. So because we're not given anything about Q3, the reasonable assumption is that we don't need that kind of information, but we better be able to explain why we don't need that information as we go through the problem. So basically, if we're putting charges in a line, it's going to be somewhere either in region 1, which is to the left of the +4. It's going to be region 2, which is between the +1 and the -1, or somewhere over in region 3, which is to the right of the -1. So let's just start with region 1. If we have a positive charge, and let's just make the assumption that it's going to be a positive charge, then if we place that third charge in region 1, you'll notice that we're very close to a large positive charge and far from a smaller charge, positive or negative. In this case, it's negative. And what that means is that this +4 will always be the dominating force. Nowhere to the left of that +4 charge is there going to be a place where the negative charge is an equal size force. So region 1 is out. If we look at region 2, then we could, we might use the reasoning, well, if we get closer to the -1, then -1 eventually is going to have a force which is equal in size to the +4. And that is a true statement, but let's consider this. It's a positive charge. It's going to be repelled to the right by the +4 and attracted to the right by the -1. So nowhere in region 2 do you have equilibrium. And then you get into region 3. And in region 3, we have the -1 is going to be pulling the positive charge to the left, and the +4 is going to be pushing the positive charge to the right. And so somewhere to the right of the -1 charge is going to be a place where there is equilibrium. Not only are the forces equal, but they are also in the opposite directions. So we know out here somewhere is where it's going to be located. Now, had this been a negative charge, all the same reasoning still applies. Okay, we have a positive, well, if this is a negative charge, well, let's start with the positive charge first. If it's a positive charge, then the force due to the +4 is going to be to the right. So we'll just say the force of 4 is to the right, and then the force of the -1 is to the left. If it happens to be a negative charge, then it's a repulsive force due to the -1 and an attractive force due to the +4. But you see there's still an equilibrium and they're still in opposite directions. And so that's why the sign of the charge doesn't matter. Okay, so now that we figured out in what region it's going to be, before we can start setting up our problem, we need to know where are things located. We have to have a coordinate system. All right, so the typical coordinate system is going to be that this is x equals 0 and that this is x equals 1. That's going to be the easiest way to do it. If you wanted to put x equals 0 anywhere else, you could do it, but it's going to be a lot more difficult if you do it that way. We are ready to start setting up our problem. Now we've identified this as a force interaction, which means we're going to start with Newton's second law. So we write F net is equal to ma. The acceleration is 0 because we're in equilibrium. And looking at our free body diagram, we're going to write F net. So we get the force of 4 minus the force of 1 is equal to 0. Now, these forces are described by Coulomb's law. This is where the definition of Coulomb's law comes in. And so what we get is K Q4 times Q, that test charge, divided by the distance from the 4 nanocoulomb charge to this location. So for right now, I'm just going to write that as R4 squared minus K Q minus 1 times Q, our test charge, that third charge. In fact, why don't we call that Q3, because that's what it was, Q3. And whether it's a positive Q or lowercase q doesn't matter. And we're going to say that this is R1 squared is equal to 0. Okay, so the first thing you should see right away mathematically is that some of this stuff goes away. We don't need Coulomb's constant. That's going to cancel out. And Q3, which is our test charge, which we don't know anything about, that's going to go away as well. And so what that leaves us with is just the distance from each of these charges to this location and the value for each of these charges. At this point, we do not need to write this in coulombs. We can leave this as nanocoulombs because this is all going to be ratios, and Coulomb's constant goes away, which is really what forces you to have to use coulombs. And so we could just use 4 and minus 1. And actually, we won't use the minus 1. And the reason we won't do that is because we already took care of the direction of the force. And so, and with this here, we took care of the direction of the force. And so we don't want to do a double negative anywhere. So you have to keep that in mind. Okay. Now we just need to finish solving this, setting this up. And the one thing we don't know yet is what is R4 and what is R1. The distance for R4 is going to be easy. We're going to say the distance from R4 to the location of that charge is just x. That's going to be our distance. And the distance from the negative charge to that location, this distance right here, this is going to be x minus 1. So let's rewrite, and we get Q4 over R4, which we now said was x, and that quantity is squared, minus Q1 over R1, and R1 is the quantity x minus 1 squared, and that's equal to 0. So now all we have to do is expand this expression and simplify it. And I think you can see that this is going to turn into a quadratic. So we have Q4 over x squared is equal to Q1 over x squared minus 2x plus 1. And now we're going to put all of our x's on one side of the equation. Let's do this up here. So we get Q4 times x squared minus 2x plus 1 is equal to Q1 x squared. Now moving this over, we get Q4 times x squared minus 2x plus 1 minus Q1 x squared is equal to 0. And now we expand out this expression here, this part of it. We get Q4x squared minus 2Q4x plus Q4 minus Q1x squared is equal to 0. We will combine all the like terms, so we get Q4x squared minus Q1x squared. And let me just do this like this. Don't have to at this point. Minus 2Q4x plus Q4 is equal to 0. All right, and now we can simplify this, and we get Q4 minus Q1 times x squared minus 2Q4x plus Q4. Now we'll substitute our values, and this is where we have to be careful. Remember, we already took direction into account, and we want to ignore the positive and negative attributes of our charges, and we're just going to use magnitudes only. So this becomes 4 minus 1 x squared minus 2 times 4x plus 4 is equal to 0. So we get 3x squared minus 8x plus 4 is equal to 0. And now there's a number of ways that you can solve this. You can factor, you can use the quadratic formula, or you can use graphing, to find your zeros. And what you're going to get is two answers for x. X is going to be equal to 2/3 and 2. And the units here, because x was all done in meters, the units are going to be in meters. So now the question is, are you going to use 2/3 or 2? The correct response here is going to be 2. Remember that the distance between +4 and -1 is only 1 meter. And that the way x is defined, it's going to be the distance from the +4 charge all the way over to the right, somewhere to the right of the -1 charge. And so if we were to use the 2/3, that's going to give us a location that's right about here. And that's not the correct location. So what does that 2/3 really mean? The 2/3 represents where the size of the two forces due to the +4 and the -1 are equal in magnitude. But remember that in this region, they both pointed in the same direction. So it's the same size force, but it's the same direction. The value of 2 meters is in the region where the two forces oppose each other once again. So the correct answer is going to be 2 meters.